Okay, so this is part 4 of the beam section. This one I'm going to do some example problems on internal loads. And we're going to start right from a beam where we don't know any information. So the external loads, we'll find those. And then we'll find any internal loads that we're being asked to find. So we have a bit of work in each of these problems, and we'll go through one by one and see how we're doing. So we'll get some strategies for solving them. Okay, so here's the first one. I consider this, if you're doing internal loads, this is the easiest problem you can get. So you should not be scared that it's a cantilever beam and it's a little weird. We are going to find this is the easiest beam to analyze. So this is the question that you should be hoping to get on your TSSA exams or on our tests in class. So this cantilever beam has a couple of loads on it, 30 kilonewtons and 20 kilonewtons, and it's attached to the wall at A. And so I've asked in this question, determine the internal loads at 2 meters and 1 meter from the end of the beam. Okay, so I got my question set up. One thing that's really easy for you about cantilever beams and finding internal loads in them is that only in very rare cases do I even have to find the reaction at the wall. Because what ends up happening is we cut this beam. So when we cut this beam, and for instance at the 2 meter mark, I guess is somewhere in here, would be the first cut. And I draw my left hand side, and it's going to look like the wall with then a section of beam, and then and I have my right hand side, which looks like this, I guess with the 30 and the 20. And I replace at the cut with a V and an M, and again V, sure, and V down, and M, so I'll go that way, and equal and opposite in that direction. What we can see is that I don't even need to know what were my reactions at the wall, which again is another set of V and M, different than the ones that are at my cut. So I don't even need to use this whole mess. And if I just concentrate on the right hand side where I've sliced, it's just like me having a cantilever beam, and now the wall is here. And we know how to approach that. So same strategy, we make our pivot point or our reference point at the cut, and we find our dimensions. So I guess it's 1.4 between the 20 and the 30, which means to get to 2 meters that would be like 0.6, and this would be my 2 meter. Sum of forces up has to equal sum of the forces down. So in this case, I guess, look at that, I got nothing that I've assigned to push up is going to be equal to V plus 30 kilonewtons plus 20 kilonewtons, and I guess V in this case negative 50 kilonewtons. Okay. And you may get different signs. So I got negative there, and you may get positive 50, and it would all come down to which direction you assigned V in the first place. So what I am interested in is that you can get the magnitude correct, and the negative or positive, as long as you have the magnitude correct, doesn't really matter in these questions at this level. As you go further in strength of materials, there is some good practices for positive and negative values, but basically you're switching over to more of a vector style calculation as opposed to having just our scalar style like we have here. I also have my sum of moments is going to be equal to my sum of moments. So going in the right hand side, I guess the same idea. I got m plus 30 kilonewtons at 0.6 meters plus 20 kilonewtons at 2.0 meters is equal to 0. And let's see, 30 times 0.6 plus 20 times 2 gives me an m value in this case of negative 58 kilonewton meters, or 58,000 newton meters. Sorry, negative 58,000 newton meters. Okay, so I have my two values. This question's probably even easier if I'm at the 1 meter mark. So at the 1 meter mark, my beam would look like this. Okay, cut it there, and I've got quite a complicated beam on this side with different forces. This one, all I have is the 20 pushing down. My beam is 1 meter. And again, assigning at that interface, and I'll keep the same convention, I guess V pushing down and M pushing up. And what that leaves me with is sum of forces up is equal to sum of forces down. So up is nothing, is equal to V pushing down plus 20 kilonewtons pushing down, and V is equal to negative 20 kilonewtons. My sum of moments is going to be equal to, sum of moments. So going in that direction, I have an m plus 20 at 1 meter is equal to 0. My m is equal to 20 kilonewton meters. Negative. All right. So I can get through an entire question pretty quickly. I don't have to go to the detail of finding all of my my external loads if I'm just dealing with a cantilever section of beam. And if I choose the free end, then it makes it very easy for my calculations. It's just like having a shortened cantilever beam that's fixed to the wall. Okay, here's a problem that I'd consider to be average in difficulty for this section. There's a lot going on. Even though it's an average problem, it is a hard problem. There is a lot to keep track of. So we have a simply supported beam, and we're going to ask for some internal load at different points. Okay, B could be a spot maybe I'd ask, or maybe the midpoint of the beam, but we should be able to answer anywhere on the beam what is the internal load. All right, so there is a bit of a shortcut if you're being asked B. That actually ends up being fairly easy. However, the midpoint part of the question is pretty tricky. So let's take a look at it and we'll work through it together. Okay, so I want it to have two spots where I find my load. One of them is right at B, okay, and then another one here at the midpoint of the beam. Okay, so as I said, B was actually fairly easy, and let me explain why. So if we cut the beam, so normally we're going to go to the extent of finding out all of the external loads happening on this beam and then be able to solve it. But actually, if we look at B, when we cut it, we have a free end. So that end is overhanging, and it's not much different than a cantilever beam. So if I was to find B and just look at the left-hand side, what I have is my section of beam. I have 30 kilonewtons pushing down. And then I could include my reaction force at B, but as we said, maybe we don't. And so if I'm just trying to find the moment, or one of my values for V, then I'm able to just solve it without finding all of my internal loads. I just won't put that internal load on my free body diagram. But I do need to have a V and an M. So I'm going to put down, just put it going up. Sure, I'll go up for my V, and then I have an M, and it's usually the convention is to move it upwards, in this case for a left-hand side, counterclockwise. So sum of forces up is going to be equal to all my forces down. So up is V, and down is 30 kilonewtons, and I have one of my answers for V. My sum of moments in one direction has to equal my sum of moments in the other direction. So starting from my pivot point, I have an M, which is going counterclockwise, and as I work my way across, I have 30, which is also counterclockwise, and it's at a distance of 1 meter, and I have nothing going the other way, so in this case M is going to be equal to negative 30 kilonewton meters. And I have my answer for M. So that can be an easy question if I'm just dealing with the overhanging end. I don't need to find all of my reaction forces. However, because I've asked you for one inside at the midpoint, I'm going to have to find some of these unknowns. Okay, so we have to go back to what we learned in the last section, part 2, and we're going to start out with number 1, my distributed load. So that's where I'm always going to start these problems. So 50 kilonewtons times 1.5 meters is going to be equal to 75 kilonewtons, and that would be at, I guess, 0.75 meters from either C or D. Okay. Number 2, I'm going to draw a new free body diagram. And my new free body diagram is going to look like this, with a 30, with my reaction at B. I have a 40, I have this 75, and then I have D pushing up. Step number 3, I'm going to pick a point, and my criteria for picking a point is usually number 1, pick an unknown force, so either B or D, but give preference to a force that's at an end. So I think D is going to be my reference point, and I'm going to pick D. Okay. I probably didn't leave enough space there. I'm going to go, maybe try that. All right, and number 4, I need to do some dimensions. So I'm going to go from D, 0.75, to the 40 load is 1.5, to B is 3, and all the way across is 4. because this is a simply supported beam, my step number 5 is going to be my sum of moments. Okay, so sum of moments in one direction has to equal sum of moments in the opposite direction. So I'm going to start at D and work my way across. First one I get to is the 75, and it is in the counterclockwise direction. So I'm going to put it on this side. So 75 at a distance of 0.75 plus. Keep moving across. So 40, and that's at a distance of 1.5. Keep moving across. Oh, I got B, and he's coming up the other way. So B at a distance of 3. And keep going across, and then down, and I have 30 at a distance of 4. So B at 3 is going to be equal to 56.25 plus 60 plus 120. So B at 3 is going to be equal to 236.25 kilonewton meters, and B is going to be equal to 78.75 kilonewtons. Step number 6, sum of forces. So sum of forces up has to equal sum of forces down. So as I go across, I'm going to start at D. I've got D down is a 75, down is a 40, up is a B, and then down is 30. So that was as I moved left or right to left across that beam. I'm going to substitute B in down here, and what I'm going to have is D is equal to 75 plus 40 plus 30 minus 78.75, 66.25 kilonewtons. Okay. So, are we done? No, we've only found at this point the external loads. So now we need to find our internal loads. Okay. I'm going to transpose this over to this drawing, and then we're going to make a bit more space. So 78.75 for B, and D 66.25. Okay. So when we do our internal loads, what we're going to do is slice our beam. And what we'd be left with is a left-hand side, 78.75 and 30. And we'll have our V and our M. Or we had our right-hand side. And our right-hand side looks like this. It's got the distributed load, and it's got a 40. That's 50 kilonewtons per meter. And we had 66.25. And we had a V up and an M going back this way. Okay, so my advice is usually don't mess with the distributed loads if you can, and we'll see in another example that they can cause you a lot of grief. So let's just use the left-hand side. So my left-hand side looks like this. 30, 78.25, 78.75. I have my pivot point, I have my V, I've got my M. Distances from that pivot. So the whole section is 2 meters long, and it's 1 meter to B, and 2 meters all the way across. Sum of forces up is equal to sum of forces down. So as I go across, I have a V pushing down. I have a 78.75 up. And then I have a 30 pushing down. Net result, 48.75 kilonewtons is going to be equal to my V. Sum of moments in one direction has to equal the sum of moments in the opposite direction. Start at my point. Always start by placing an M. So M is going counterclockwise. Come across. I have this guy going the opposite direction. 78.75 at 1. And then make my way to the end. And I have my 30. So 78.75 minus 30, and I have an M value. Oh, isn't that interesting? 48.75 kilonewton meters is equal to M. All right, so I have my two answers, and I found that load. This all takes a lot of work. It all takes a number of steps. We just go back and review our steps. 1, we have a distributed load. We have to do a distributed load. And all of this is to find our external loads. So this was old content. Okay, but this is the pathway that we went through to find our external loads. So we found our distributed load, we drew a free body diagram, we picked a point, we figured out our dimensions, and then we did our math with our sum of moments and sum of forces. When I went to find my internal loads, I guess I then continued on to, number 7. So cut the beam and then pick left hand side or right hand side. Number 8. V and M at cut. Number 9, your sum of forces. Number 10, sum of moments. And all of these in order to find an internal load.